Hi everyone. So I wanted to do a short video to go over some of the basic mathematical notation that we will be using this semester. This is notation that I'll use in my slides, I'll use it at the board when I'm going over material. You'll also see it in the reading material, especially in the more mathematical economics literature that we look at. So the notation that I want to go over is notation for talking about sets. Now, a set is just any collection of objects. And this semester we'll say things like the decision maker is selecting from among a menu of options. And by that we just mean a set, a collection of objects. These are the feasible objects that are available for the decision maker to choose from. Now, how do you denote a set? A set is denoted by simply listing all of its elements. So we use these curly braces here to signal that the list of objects inside of the curly braces is the set of things we're interested in. So this here is the set of numbers 1, 2, 3, and 4. Here we just listed all the elements of the set. Now we have another way to denote a set besides just listing all the elements. Namely, you can write down a property that all the elements in the set have. So for example, we still use these curly braces. So here we have the left and right curly brace that signals that what goes inside is the set of objects. So this says the set of all x, and then this line here means such that. So the set of all x such that, and now we'll write down a property that all the x in this set have. So here's the property we're interested in. X is an integer, x is greater than or equal to 0, and x is less than or equal to 5. So that's really just the set 0, 1, 2, 3, 4, and 5. So here I've listed all the elements of the set explicitly, and here I wrote down a property that all the elements of this set actually have. So that's two ways to denote the same set, namely the set of these 6 numbers, 0, 1, 2, 3, 4, and 5. Now you might wonder, why do we have two ways to write down a set? Well, the second way is very useful when you have an infinite set. So here, this is the set of all x such that x is an integer and x is greater than or equal to 0. So this is the set 0, 1, 2, 3, and so on. This is an infinite set, so I obviously can't write down all the positive integers. So this ... here really refers to this property. It's saying that's the set of all x such that x is an integer and x is greater than or equal to 0. So incidentally, this is also denoted by the script n here. So this n denotes the set of all positive integers. So one last thing I wanted to note about sets is that sets may contain other sets as their elements. So look at this set right here. This set contains 2 elements, 2 objects. The first is the number 1. The second is another set. This is the set containing 2 and 3. So this set right here contains 2 objects, 1 and another set. That set is a set containing 2 and 3. All right, so now I want to go over some examples of sets that you'll bump into this semester. So the first is the empty set. So this is denoted by a 0 with a slash through it, or a O or 0 with a slash through it. And this is the special set that does not contain any elements. So it's completely empty. That's why it's called the empty set. Another set that we'll be interested in is the set of all integers. This is the set of both negative and positive numbers, or I really should say integers. So the ... here means the set of all the negative numbers, negative integers, and this ... on the right means the set of all positive integers. Actually, we'll probably mostly be interested in the set of all positive integers. As I said, that's the set n. We also sometimes denote that by z plus to signal that it's the set of integers that are positive, including 0. So n always includes 0. We're also going to be interested in the set of real numbers. And this basically is any number that you can think of. It's the set of integers, the set of fractions, it includes the fractions, the integers, also the irrational numbers like pi and other numbers that you may have bumped into in a math class. So you really think of this as the number line, the standard number line, where you have 0, then any number to the right and any number to the left. That's the set of all real numbers. If we're just interested in the set of all positive numbers, positive real numbers, we'll write r plus. And it's by convention, but often I'll think of 0 as being an element of r plus. Two other set of integers that or real numbers that we'll be interested in is the interval 0, 1. So on the real line, we'll look at all the real numbers between 0 and 1. So we're looking at all the real numbers between 0 and 1. The square brackets here mean that we include 0 and 1 in that set. And the parentheses here mean that we do not include 0 and 1 in the set. So it's all the real numbers between 0 and 1, but not including 0 and 1 themselves. All right, so there's two bits of notation that I want to talk about involving sets. The first is what it means to be an element of. So if we write x, this sort of weird looking e, x is an element of A. So here I'm thinking of A as a set. So we have this set A. And x here is some element of A. It's contained inside of A. Now, if we were to write x is, put a slash through this E symbol, this means x is not an element of A. So that means x resides somewhere outside of this set A. So here we have the set A. X exists somewhere outside of A. So for example here, we have 1, the number 1 is an element of this set. Why? Because we see that 1 shows up in the list of elements in this set. 42 is, of course, an element of the natural numbers. It's a positive integer. D here is not an element of the set consisting of A, B, and C. So we have a set here which consists of the letters A, B, and C, and we see that D is not an element of that set. It doesn't show up in that list of sets. Here we see that 2, 3, the set containing 2 and 3, is an element of this set. Why? Because this set shows up here as one of the elements, one of the objects in the set. But note here, 1 and 2, the set containing 1 and 2, does not show up in this set. Even though you see 1 showing up there and 2 showing up in the description, but note that 2 is actually in this other set, which is contained in the bigger set. So the set consisting of 1, 2 is not an element of the set. Why? This set consists of 1 and another set, which is 2, 3. And the set containing 1, 2 is not an element of this set right here. Okay, so here we have element of. The other notion you want to be concerned with or know about is subset of. And we denote that with this symbol right here. This kind of, it looks like a rounded less than or equal symbol. So this means that x is a subset of y. So in a picture, if we have y here, saying that x is a subset of y means that all the elements of x are contained inside of y. So x is completely contained inside of y. So x is a subset of y. What that means is that if x is a subset of y, that'll happen if and only if, for any object you give me, so any element, if x is an element of capital X, then x must be an element of y. So if x is not a subset of y, what does that mean? Well, here we have x, and there's going to be some object inside of x that is not contained in this set y. So x is not a subset of y means that there's some object x such that x is inside of capital X, but x is not inside of y. It's not an element of y. So to give an example, here we see that the set containing 1, 2 is a subset of this bigger set 1, 2, 3, 4. Why? Because for any object, if it's in this smaller set, so we have two objects to be concerned with, namely 1 and 2, and I see that 1 shows up here and 2 also shows up there. Note that here we have 1, 5 is not an element of this set. Why is that? Well, there is an object 5, which is an element of this set right here. So 5 is an element of this set, but 5 doesn't show up in the set 1, 2, 3, 4. So we see that 1, 5 is not a subset of the set containing 1, 2, 3, 4. Notice here that 2, 3, the set containing 2, 3, is an element of this set right here, because here we have 2, 3 is an element of this set, but 2, 3 is not a subset of that set. Why? Because in order for 2, 3 to be a subset of this set, we would need both 2 and 3 to show up in this set, and they don't show up in this set. It's important to remember that, because here we have this bigger set right here contains 2 objects, namely 1, and then the set consisting of 2 and 3. But the number 2 is not equal to the set consisting of 2 and 3. And finally, here we do have that the set consisting of just 1 is a subset of the set consisting of 1 and the set consisting of 2 and 3. Why? Because every object here, namely 1, does show up in this set. So we see that 1 shows up here. Whereas up here, we saw that 2, for example, doesn't show up in this set because it's the set 1 and then another set consisting of 2 and 3. Okay, so that's subset of. And it's really important to distinguish between element of and subset of. This is something that beginners often have trouble distinguishing between these two notions. Both of them have the idea that if something's an element of another set, you think of it as being contained in the other set. And if something's a subset of, you also can think of it in some way as being contained in the larger set. So note here, 1 is an element of the set 1, 2, 3, 4. But 1, of course, is not a subset of 1, 2, 3, 4. That's just incorrect notation. In fact, if you were to write this down, and this is something that I often see a mistake that's made in the mathematical notation, this notation is completely incorrect, because an element can't really be a subset of a set. But we do have, if I were to put 1 into a set itself, so the singleton 1, so this says the set containing 1, that is a subset of the set containing 1, 2, 3, 4. So just to kind of drive this idea home, consider the set of all humans. So here we have the set. This is the set of all humans. Right? So this is the set of all humans. And you might think of, let's say, the set of women, people who identify as women. So here we have the set of women. Now, the set of women is a subset of the set of all humans, but of course the set of women is not an element of the set of humans, because the set of women is not itself a woman. So that wouldn't be an element of the set of all humans. Okay, so it's important to distinguish between element of and subset of, and a few other things that I want to note. So first of all, we are going to write x equals y when x and y simply have the same elements. Now, when you write down sets, the order that you write down the elements doesn't matter. So the set consisting of 1, 2, 3 is the same as the set consisting of 3, 1, 2. So I wrote they each have the same element. So 1 shows up in both, 2 shows up in both, and 3 shows up in both. But of course here, note 1, 2, 3 is not equal to the set consisting of 1 and then another set that happens to contain 2 and 3. So what we have is the property you have to remember is that x is equal to y if and only if both x is a subset of y and y is a subset of x. Because if x is a subset of y, then every element of x is also contained in y. But if y is a subset of x, then every element in y is also contained in x. So that means that I can't find an element which is in x but not in y, or in y but not in x, so they have to have the same set of elements. The important thing to remember is that when we use curly braces here, the order in which you write down the elements does not matter. Another thing I want you to note is that the empty set is always a subset of any set you give me. So it doesn't matter what set it is, namely the empty set itself. The empty set is always a subset of that set. Now, why is that? Well, we have two options. So given any set x, the empty set either is a subset of x or the empty set is not a subset of x. So there are two logical possibilities. Either the empty set is a subset of x or the empty set is not a subset of x. So one of these must actually hold. So let's think about, could it be that the empty set is not an element of X? Well, if the empty set is not a subset of X. So for the empty set not to be a subset of X, there has to be an element X that is in the empty set, and X is not in capital X. Well, that can't happen. There can't be an object that witnesses the fact that the empty set is not a subset of X, because the empty set doesn't contain any elements. So since this possibility can't happen, it must be the case that the empty set is a subset of X. And also, it should be not too hard to see that X is always a subset of itself. Now, one final piece of notation is the notion of a power set. So the power set, with this sort of funny looking P, the power set of X, that's the set of all Y such that Y is a subset of X. So for example, the power set of 1, 2, 3 consists of these 8 objects: the empty set, the set itself, the set consisting of 1, consisting of 2, consisting of 3, and these 2 element sets. So to figure out what the power set is, we have the set 1, 2, 3, and I ask for 1, is 1 an element of the set, or is it not an element of the set? And then you ask, what about 2? Is 2 an element of the set, yes or no? So we say maybe it is, maybe it isn't, maybe it is, maybe it isn't. And then we can finally ask for 3. Is 3 an element of the set? So we ask about 3. And again, for 3, we can say either yes or no. So yes, no, or yes and no. So for example, if we say, is 1 an element of the subset? The answer is no. Is 2 an element? The answer is no. Is 3 an element? The answer is no. Well, this tells us that this leads to the empty set. So nothing. The empty set is a subset of the set 1, 2, 3. And here, if we say, is 1 an element of the subset? Is 2 an element? Yes. And is 3 an element? Yet. If we say yes to all of them, we get 1, 2, 3. And for example, if we were to follow, say, this path right here, so 1 is an element, but 2 is not an element, yet 3 is an element, we would end up with the set 1, 3. So as an exercise, it might be useful to write down the sets that each of these paths actually lead to. So this is the notion of a power set. And it'll show up from time to time throughout the semester. So this is just some of the basic notation for reasoning or talking about sets that we will use this semester. There's some quizzes and other homework that might help you clear up some of these ideas. All right, so hopefully this is helpful, and please let me know if you have any questions.